So for the next step, step 4, we're going to find the stationary points, which are the turning points. And that's where the derivative f dash of x is equal to 0. So first of all, let's find f dash of x. So we take our original equation, which is up here, the cubic, and we differentiate it. And we find the derived equation. So we say f dash of x equals, and you need to know how to differentiate. So basically it's quite short and, what's the word I want to use? Intuitive. So it's not anything hard. So this is how we differentiate. So this is x cubed. So we drop the 3 to the front of the x and we make it from a cubed to a 2. So in other words, we drop the power by 1. For the next term, we take the squared term that's sitting above the x and we multiply it by the coefficient in front, the 6. So that makes it 12. And then the power above the x is 1 less than what it originally was, so it's squared. And so it becomes a 1. So we don't have to draw a 1, we can just leave it as 12x. The final term is like a linear term, so this doesn't have a higher power than just x1. And what would happen with this, we could go 9 times 1, and then the power would go from 1 to 0, which makes the whole thing 1. So we end up with plus 9. Okay, there's no x term. It's kind of basically fallen off because x to the 1 becomes x to the 0, and that's the same as times 1. So that's 9 times 1 is 9. Okay, so you'll notice when we differentiate, each power ends up 1 power lower, and where the x is just ends up with no x. So that does end up 1 power lower as well. So now that's the derived equation, and we can tick off one of those steps. Well, not quite yet because we haven't found the stationary point. We've done the derivation. So now we need to set this equation, this derived equation, f dash of x to equal 0. So we're solving again. We're solving a polynomial. So 3x squared plus 12x plus 9 has a gradient of 0. So what this means, just to give you a little bit of context, is we're finding these sorts of points here where the function is turning around, okay, in its gradient. So we're finding these actual points where it's changing from a negative to a positive gradient or a positive to a negative gradient at the 0 gradient. So these points turn when the gradient is like this horizontal. And so f dash of x finds the position of that, setting it to 0, to a 0 gradient, finds where that x is, what that point is. So we're finding the points of the turning points. We're finding the positions of the turning points. So let's go ahead and solve this now that we have done it. And that is our f dash of x equals to all that. So when I stare at this now, I notice that it's not straightforward to put into brackets, although I'd like to. So I just stare at it a little bit longer and I can see there's a common factor of 3 and x, or just 3 actually, in that. So I'm going to take out the common factor of 3. So 3, and then I'm going to do a bracket for the remaining terms. So we have an x squared plus 4x plus 3. Okay, so I've taken the 3 out. It still equals 0. Now, because I have a squared term with no coefficients, I'm hunting now to get it into 2 brackets. So I'm hunting for 2 numbers that multiply to 3 and add to 4. So plus 3 and x plus 1. So I factorize that now, which helps me to solve it. And using the null hypothesis, this whole thing is 0 when either this bracket is equal to 0 or the second bracket is equal to 0. So when x plus 3 is 0, or when x plus 1 equals 0. So that means x is either equal to negative 3 or x is equal to negative 1. So to locate those points on my graphs, I've only so far got x values. And what I need to do to plot them and to find where the turning points are is I need to put these values back into the original equation. So my first derivative's done its job now to find the turning point. Please note we haven't found any points of inflection necessarily. We've just found the very strict turning points where we have a horizontal gradient and we're yet to go to the inflection point part, but we're finding the turning points or the stationary inflection points. So we're sort of finding part of what we need, and we've found part of what we need to plot. So we're going to be putting these values back into the absolutely original equation. So I'm going to write it like this, f of -3. Notice it's not f dash, it's f. It's going to be the first equation where I'm just going to substitute -3 for the squared plus 6 times the x value, -3 squared plus 9 times -3. Okay, just a blooper there, but I've stopped and adjusted it. That should be -3 all cubed. So as we work that equation through, we figure that the final answer for that equation is 0. Hence, one of our stationary points is -3 and 0. So we actually already had that one on the graph because it was actually a root or an x solution with that 0 that you might recognize there, but that's okay. This is part of the process of working through all the steps. It won't always be 0 when you do stationary points as such, but this just means that one of the turning points is on the x-axis, and we found the one that we identified before. Let's work through this one now. For x is -1, we're going to plug and play -1 into the original equation, which is x cubed. So let's do it color-wise, how we did the other side. So that's -1 all cubed, plus 6 times -1 squared, plus 9 times -1. Equaling 4. So our second stationary point that we found in this process is -1 for the x and 4 for the y. So we can go ahead and plot these points also on our previous graph. So at -3, 0, we already had that as intercept point, but we're just going to just mark that there. And at -1, -4, we're going to put the other point there. So we're on the way to sketching this thing now that we've done the turning points. So we have found the turning points. We certainly haven't done any testing on those turning points, any derivative testing using first or second, but we have just identified the actual points themselves. So the next video will look at how do we use this derivative business to identify the nature of the turning points so that we can continue to build